Hi class, so we're going to be doing a shorter section called 2.3, and it's about valid argument forms. We're using truth tables again. We're using some new terminology called modus ponens and modus tollens. And then we'll also be finishing up with learning about a couple fallacies called the converse error and the inverse error. And again, all of this is just the building blocks so that we know how to argue well when we're doing proofs and algorithms and stuff like that. So let me share my screen and we'll go into the notes. And I have these notes again on Canvas, so you can take a look and take a look at that. But here we go, section 2.3, valid and invalid arguments. So when we have an argument, what does an argument mean? It means you have some amount of premises and a conclusion. Remember that? So it was like, P, let me start drawing here. You have, P and then Q, or say P and Q, Q, therefore I have not P. Now this is an invalid argument. Well, we're going to see why, but still it's an argument because it has premises. So these are the two premises here, premise number one, premise number two, and this is the conclusion. We'll learn some terminology. This first one's called the major and the minor, or the major premise, the minor premise. But anyways, how do we tell if an argument, and the entire thing is called argument form, how do we tell if an argument form is valid? So basically, how do we tell if we're making logical things here? How do we know our conclusion is true? Well, the way you do is that you identify the premise and the conclusion, in symbolic form, so you can write it out like this. And then you want to construct a truth table, okay? And like usual, you just show all the truth values for the premises. That's like the automatic part, okay, and also the conclusion. And a row of the truth table where all the premises are true is called a critical row. So what we're going to do is we're going to take a look at where all the premises are true. And if there is a critical row in which the conclusion is false, so basically if we have true leading to false, okay, that's going to tell us that means the argument is invalid. The entire argument form is invalid. I shouldn't say really leading to false, but I should say true. If I have true premises, but I have leading to a false conclusion on the same row, then that's going to tell me that the whole argument is invalid. And as long as one row is invalid, that means that the whole argument is invalid. So let's take a look. Let's determine this one. Determine whether the following argument form is valid or invalid by drawing a truth table. So again, to terminology here, this is premise. These are the premises here. So premise number one, premise number two, and then this is the conclusion. So luckily we have a truth table because it's hard to tell if this argument is valid or not. It's kind of long-winded. It says, okay, if P, then P implies Q or not R. Q implies P and R. Therefore, can I conclude that P implies R? I think if I thought about it for a while, I'd be able to think about it and come to say if this is a valid or invalid argument form. But luckily, we have a truth table because a truth table will help us decide. Table really helps. Will really help us decide if this is a valid or invalid form. So to save some time, because the video's been going kind of long, I wrote out the truth table here. But let me zoom in a little bit here. So what you do is, if you look back on that argument form, we had two premises and we had a conclusion, but also we had how many statement variables? We had three. So we had three statement variables here. So these are the statement variables. So we're going to have then 2 to the power of 3. We're going to have 8 rows. So this is row number 1, row 2, row 3, dot down to row 8. Okay, and then it's just like building up like we've always been. So this is the automatic, what I've been calling the automatic in the other videos. So we just fill that out, just True, 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 false. That's like what we do. Then we also, this is like the not R here. Okay, we need the not R because we had not R in one of the premises. So we just do it. And again, remember this just flips. So this just is the opposite of R. So whatever R was, R true becomes false, false becomes true, etc. Okay, and then again, we just start looking. And remember, or is true uh, um, when one of them is true, or both. So all again is we just look at Q. Okay, anytime I have Q, then this or statement is true. So true, 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 true. And then also it's going to be true when I have not R. So when is not R true? Okay, true, 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 and true, true. So I have 1, 2, 3, 4, 5, 6 rows where that's true. Okay, and then I look at PNR. These three things in general aren't the premises, but they're the building blocks of the premise, because the premise had a P, it had a Q or not R, which is right here, and it had a PNR. So I need them. And then you just go down again and do the ands. Okay, I'm not going to do it all, but this is only going to be true when P and R are both true. So you just find out where that is. Okay, it only happens two times. Here and here. Okay, and then you fill out the premises. Now, remember, how does a hypothesis, how does a if-then, a conditional be true? Well, anytime I have true leading to true, or false leading to true, or false leading to false. So as long as I have a true P here, this uh, as long as I have true leading to true, I'm going to be okay. So do I have true leading to true? Yes, so that's good. Do I have true leading to true? Yes, that's good. Okay. And then it's also true when I have a false conclusion. So a false, first thing, when P is false. So anytime P is false, right here, 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 this is guaranteed to be true. So boom, boom, boom. So that's great. And then the last one is we look at, oh, I missed this one, when I have true P leading to a true Q or not R. So that's there. Okay, so these are the vacuously true ones. Okay, so I only have one part here where the premise was false, which is P implies Q or not R. Anyways, I'm gonna kind of go a little bit faster, but you can do the same thing for this conditional Q implying P and R. This is going to be true, like I said, same deal. It's only false when I have true leading to false. So we'll look for the row where you have a true Q leading to a false P and R, which would be right here, this row. That's going to be false. And then also down here on row, on row, well, you can kind of see it there. Let me back up a little bit. On row 5 and 6. So I have false here and here, but the rest are true. Okay, now to worry about the argument form, all we care about is look at the row, look for the critical rows. Okay, and that's where I have true premises and true conclusion. Okay, let me back up here to the definition again. So I want, where the premises are true, I don't care about the conclusion. I need to check the conclusion. So just look for the true premises, okay? So I'm gonna circle the rows where I have both premises being true. So that's true, and then these both are true. So row 1, 4, 7, and 8. And then you just look at the conclusion, P implying R. Again, you have to work out when is P implying R true. Well, P is going to imply R is going to be true, when either P is false or when I have true P and true R. So you just look for that in the table. And here, true, okay. Here, false leading to true, because that's vacuously true. So these are vacuous. But the bad row is right here, row number 4. Because on this row, it's a critical row, I have true premises, but I had a false conclusion. So I have true premises and a false conclusion. So one row of the truth table had false true premises and false conclusion. So the entire argument form is invalid. Pretty harsh, right? The argument form has to be true, has to be valid. To be valid, has to be true on every critical row. It can't have a true premises leading to a false conclusion. Okay, so I'll let you go back and take a look at that and try it on your own. I do recommend trying it on your own, where you remove all these right side stuff, just start with the automatics and make sure you can fill it out. Moving on, modus ponens and modus tollens. So these are valid argument forms, and they're a special form called a syllogism. Syllogism just means that you have two premises, a major and a minor. The major is the first. So this is the major premise. This is the minor. This terminology is not that important. And then you have the conclusion. So modus ponens is the most famous one. And what it says is that if P then Q, I also have P, and then you can say, therefore, I have Q. Famous one, as you will hear in every single logic class ever taken, is that all men are mortal, which, so that's like the first, the major premise. Then the second premise is that Socrates is a man. You can say, therefore, Socrates is mortal. We'll get to that into a sec. We haven't gotten to that, but you can rewrite it all men are mortal. It's equivalent to saying if you're a man, then you're mortal. And by the way, that man is not gendered. It just means you're a human. You know, if you're a man, then you're mortal. Okay, so this is modus ponens. Basically, if P then Q, I also have P. Therefore, I'm allowed to conclude that I have Q. Modus tollens is just the same thing, but in contrapositive form. What it says is that, again, the major premise is that if P then Q, I have not P. Oh, shoot, this is backwards. Sorry, these notes are wrong. It's not Q. Therefore, I'm allowed to conclude not P. This, again, is just contrapositive, because the contrapositive form of P implies Q is not Q implies not P. So the modus tollens is just the modus ponens version of the contrapositive of the original statement, P implies Q. So if P then Q, if I have not Q, then by this thing, I can say, therefore, I have not P, just by contrapositive. But it has a fancy name. It's called modus tollens. And sorry about this error here. Okay. Let's jump into example. So here's an argument of this form. If the sum of the digits of blah, 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 blah is divisible by 3, then it's divisible by 3. So this is the if P then Q part. So P implies Q. Now what do I have here? The sum of the digits is divisible by 3. So this is, I have P here. So again, modus ponens said if you have P implies Q, if you have P, then you're allowed to conclude Q. So this is saying I'm allowed to conclude Q. So that's what we're able to do there. Let's get practice here. Blah, blah, blah. So let's see if we're going to use modus ponens or modus tollens. So this says if there are more pigeons than there are pigeonholes. Okay, so that's an if. So this is going to be the P part. Then Q. There are more pigeons than there are pigeonholes. So that's going to be P. So again, symbolically, I'm having the first premise is P implies Q. The next premise is that I have P. There are more pigeons. So what am I allowed to conclude? I'm allowed to conclude Q. So in words, I would say there are more pigeons. Sorry, at least 2 pigeons. I didn't do Q. Oop. At least 2 pigeons roost in the same hole, which is just Q right here. Let's look at this one. If blah, blah, blah is divisible by 6, okay, so that's P, then Q. I have the number is not divisible by 3. Well, guess what? That is not Q. So what do I have here in this argument? I have P implies Q. I have not Q. So what am I allowed to conclude? I'm allowed to conclude not P, which is the contrapositive, the not negation of P. So I'm allowed to conclude not P, which is to say I'm allowed to conclude 8, 7, 232. Wow, sorry, my handwriting's bad. 870,232 is not divisible by 6. Okay, which again was the not P. Okay, so modus tollens is just the contrapositive version of modus ponens. Yes, and we have the answers there. So this is the same thing. Okay. So speeding along here. So other things is that we want to talk about rules of inference. So a rule of inference is just any argument form that is valid. Basically, it's saying that if you have a valid argument form, we can call it a rule or a rule of inference. And so anything that's valid is going to be is just a synonym for rule of inference. Okay. We're going to use a few more of these, so just good to have them. So P, and this is called the generalization ones. So P, if I have P, therefore I can say P or Q. This kind of makes sense because it's like saying, I'm Scott. Therefore I can say, therefore I can say I'm Scott or Jay-Z. Right? I mean, it makes sense. If I'm Scott, then I'm allowed to say I'm Scott or Jay-Z or Iron Man, or anything like that. Okay. And same thing with Q. This is like saying I'm Jay-Z. Then what Jay-Z is allowed to say is that he's allowed to say I'm Scott or Jay-Z. So it's kind of like a duh thing, but it's just good to know that we can do that logically. Specializations is kind of the opposite of that. So it says I'm Scott and I'm right-handed. Then I'm allowed to conclude I'm Scott. Again, this is kind of like obvious because in the first statement, I said I'm both things. So what this is allowing us to say is that if you have an and, you can then go and say, all right, you can say at least one of them. And this is the exact same thing. It just says, then you're allowed to say I'm right-handed. Again, kind of obvious, but it's good to know that we can do that. Okay. These are called the elimination. We'll also get into division into cases, but what this says is that P or Q. So this says like I'm Scott or I'm Jay-Z. I'm not Jay-Z. Well, then what are we allowed to say? Of course, we're allowed to. Of course, we have to conclude that therefore I'm Scott. And same deal here. If I said, I'm Scott or I'm Jay-Z, but then if I said I'm not Scott, then of course you'd have to conclude that the speaker would have to be Jay-Z. Again, this is just kind of obvious, but it allows us to eliminate and remove the cases. And the last one, I think it's the last one, of course, is transitivity. We've all done with this in math before, but the argument goes if P implies Q and then Q implies R as well, then that means that we can say P implies R like that. It's kind of obvious, if I say if this, then that, and then that implies that, then of course, if I start here, you can just follow the chain. And in my mind, I kind of think of it like this: P implies Q implies R. But it's kind of hard to deal with multiple conditionals, so we don't like to write that. So instead, just think of this as argument as saying that if you have these two, the first premise and the second premise, you're allowed to conclude you're allowed to conclude this, which is that P would then therefore have to imply R. All right. Here's an example. An example below, suppose n is a particular integer. Remember in symbols, that means n is in Z. If n is divisible by 18, then n is divisible by 9. Okay, so this is P implies Q. If n is divisible by 9, Q implies R, then the sum of the digits of n is divisible by 9. Okay, then the last thing must also be true. We can say if n is divisible by 18, then R, the sum of the digits is divisible by 9. So that's pretty cool. So again, this was saying P implies Q, Q implies R, then we can therefore conclude that P implies R. Okay, just transitive. This is a really, really powerful thing that we're going to be using a lot this semester, division into cases. So what does this say? Well, it actually has three premises, and the first one says P or Q. The next one says P implies R. The next one says Q implies R. Again, this is like saying I'm Scott or I'm Jay-Z. If I'm Scott, then I'm right-handed. I'm going to hope it's true that Jay-Z is right-handed, because that's what this statement would say. If I'm Jay-Z, then I'm right-handed. Since either case, Scott or Jay-Z are right-handed, then therefore we're allowed to say I'm the speaker. The speaker who's talking is allowed to say I'm right-handed. Okay. Kind of obvious if you think about it, but it's good to know that we could do that. If you have an or, then you have these two conclusions. One of them must be true because P or Q is true. So we're allowed to safely assume the conclusion that R are right-handed. I think what I'm going to have you do is actually work on this on your own. So go ahead and read this and the solution on your own. The notes are on Canvas. But check it out. It's kind of a little bit longer, and it's just going to be me reading a lot, so it'll be kind of boring to watch. But read it out and follow the logic of what the solution is doing, so that you can answer the last question, which is where are the glasses. If we were in a in-person class, I would have you all do this together. It's really fun. It's kind of like a treasure hunt, but we can't do that. So instead, just read it and then kind of go through and follow. And then I did ask a couple questions in the homework that will help you go through this on your own on problems like this, like problems about where the treasure is and stuff like that. Okay, finishing up, fallacies. Fallacy is different than a valid rule of inference because it's actually something that's wrong. A fallacy is something that results in an invalid argument. You can kind of read these here using ambiguous premises. That's like if you label a variable, but you don't say where the variable comes from, like is n an integer, is n a real number, something like that. Circular reasoning, which is assuming which is to be proved. That's a really deadly one, and we're going to be working on that together a lot this semester to make sure that you don't do that. Yeah, I won't be able to get into it now, but do that. And then jumping to a conclusion is a bad one too. That means that you jump to the conclusion without maybe making sure that you had the premises that you were supposed to. We had talked about two other fallacies. That's called a converse and inverse error. And let's bring those up again to make sure that you understand that these are fallacies as well. They're bad arguments. They're invalid arguments. So let's take a look at this one. Remember what the converse error says is that if you're the converse error says, this is true. Assume P is implies Q is true. But then you say, so P implies Q. And then the converse says, okay, I have Q, and then therefore I conclude not P. Sorry, therefore, then I assume P. Okay, this is bad. This is invalid. Okay, don't do that. I'm not saying this is a true argument or a sound argument. But this is what the converse error says, is that you work backwards. So if you have a P that implies Q, and then you start with Q, and then you can therefore say P. It's not true. So here it says if Zeke is a cheater, then Zeke sits on the back row. So that's a Q. Zeke sits on the back row, Q, therefore P. And again, this argument form was P implies Q, I have Q, and then therefore I can say P. But this is invalid. This is not true. Okay. This is arguing backwards. Okay. The first thing says Zeke, if Zeke is a cheater, then Zeke sits in the back row. But it doesn't mean that if Zeke sits in the back row that he's a cheater. Okay. He can just sit in the back row without cheating. You know, that's what this first statement says. It just says that it's sufficient that if he's a cheater, then therefore he will sit in the back row. But there's going to be chances where he sits in the back row and it doesn't mean he's a cheater. So it's invalid. Okay. So that's the converse error. And let's do one with the inverse error, and then we'll go home. If these two vertices are adjacent, then they do not have the same color. Again, this is P, Q. So this is P implies Q. What was the inverse error again? Well, what that says that P implies Q. I say not P, therefore I can conclude not Q. This is invalid argument. We did the truth table for it. Invalid. Really bad, don't do that. So this must be saying not P. Yeah, two vertices are not adjacent, so not P. Therefore, I can conclude not Q. But again, this is an invalid argument. This is the inverse error. It's a fallacy. Okay, don't do that. And here it is in symbolic form as well. Okay, we're going to be running this to lots, and I'll give examples too when we do more problems and stuff like that. But just make sure that you don't run into that. Last little bit here is that I've summarized this. This table's on Canvas as well. So these are the table of valid argument forms, and feel free to refer to these as you like. Okay. You'll have these on any test or any quiz like that too, okay? But we went through these today: modus ponens, modus tollens, generalization, specialization, conjunction, elimination, transitivity, division cases, and contradiction rule. We didn't really do that, but what that says is that if you have a something leading to a contradiction, then therefore you must have the opposite. It's not as important, doesn't come up as much, but you might see it. Okay, thanks everyone for watching. The notes will be posted on Canvas, and I will see you soon. All right, bye-bye.